there. All right, so welcome everybody to the Monday AFT seminar. Today we are very happy to have with us Akash Jain from University of Victoria in Canada, who is going to tell us about non-universal hydrodynamics. Thank you very much. I remind you that you can interrupt if you want to ask questions, or you can also use the chat if you want to ask questions to be delayed until the end. And I also remind you that this talk will appear in the IFT YouTube channel maybe in a couple of days. So thank you, Akash, and please go ahead.
Thank you, Jose, for having me here, and thank you, organizers, for this opportunity to talk. Well, today I'm going to share some results with you about some work I did with Pavel at Victoria. And this paper appeared very recently this month. So the results are quite fresh, and actually I would very much like your feedback on this as we go. So, well, the title is a little bit of a clickbait. Non-universality of hydrodynamics does not give you much information, but I hope my abstract did. So what I'll be trying to convince you in this talk is that what we know and love, that is a formulation of hydrodynamics, and pretty much any condensed matter system or any condensed matter model that we build based on certain classical equations of motion is actually not as good a description of real world as we would like to think. More sophisticatedly, in a way, what I would try to show to you that there are thermal fluctuations or stochastic fluctuations which violate the so-called universality of these models, or the universal applicability of these models, even in the regime of applicability of what we usually think is the hydrodynamic regime. So to jump right in, let me start with a big picture. Well, I would not think that I really need to explain to this audience, or most of you anyway, that why we need hydrodynamics or why do we study hydrodynamics. But at the same time, it's not a bad idea to go back to the scratchboard once in a while and just see why we are doing what we're doing. So as physicists, we would like to build models, right? We would like to build models for studying the world around us. And as it happens, the current paradigm, like the current state of the art for doing so, for building such models, is quantum field theory. What you typically do is, like, the most concrete thing you can do is write down a so-called effective action for the model you're interested in. You isolate certain symmetries that the system enjoys, you isolate certain degrees of freedom, you write down an effective action, and that's your starting point. Then you can use a variational principle to derive your equations of motion, or you can do more sophisticated things like compute S matrix elements or compute correlation functions of various things. However, this is not, I mean, at least I did not realize it up until a couple of years ago, that the conventional formulation of hydrodynamics is actually, of quantum field theory, sorry, is quite restrictive in that sense, that it only allows you to study fluctuations around the vacuum state. So you can study things like, I don't know, they are the sandwiches of the vacuum operator. So you can compute vacuum expectation values of various things. You can compute S matrix elements. But these are all questions that you can ask about perturbations around the vacuum state. In particular, if you were in a finite energy state or a finite temperature state, the usual quantum field theory is not the best framework to go about it, just because it perturbs around the vacuum state. But what you can do is, at least if you're only interested in equilibrium phenomena, that is, things are not time dependent, everything is static, then you can use statistical field theory, which is that you Wick rotate the time coordinate, which is like a technical thing you do. At the end of the day, what you do is, like, you write down a Euclidean field theory, you write down a partition function as almost a Euclidean effective action, and then you use this to build any model that you might want. And this is pretty much the starting point of most modern condensed matter field theories or condensed matter systems that we see around us. However, this is still will not allow you to go out of equilibrium. You still need to do a lot of other tricks if you wanted to go out of equilibrium. And the most prominent, I mean, if you knew the microscopic theory exactly, you could go out of equilibrium using the so-called SCHWINGER-KELDYSH formalism of thermal field theories. But if you wanted to build effective models, then this is still not the best place to start, because we don't know how to deal with dissipation. We don't know how to deal with like essentially thermal noise that becomes important as you go out of equilibrium. So this is basically where hydrodynamics comes in to our rescue. What it tells us is that, okay, well, we might not know how to go exactly very far from equilibrium or how to set up out of equilibrium theories in general. But what we do know is that how should we think, I mean, how can we perturbatively depart from equilibrium? So if we know our equilibrium theory, if we know what our generating function or partition function is in equilibrium, then we can perturbatively depart from equilibrium using hydrodynamics. And it's a pretty universal theory. And the idea behind this is essentially that whenever you do a perturbation in your equilibrium state, thermodynamic equilibrium state, if that perturbation excites any degrees of freedom that are not conserved, then they will locally dissipate. They will locally die down and pass their energy to individual molecules and maybe increase the temperature of the entire state or something. However, if you were to excite any conserved quantity, for instance, you take a box of gas and you put in some particles into it, this is not going to dissipate locally, and just because the number density is usually conserved. And the only way for the system to thermalize is that these extra particles that you put in the system at some space point are going to travel to all the far regimes of the box and going to eventually equilibrate to have some average number density everywhere. And hydrodynamics is essentially the theory which characterizes how these conserved fluctuations move around in the fluid. And it is expected that if you wait for long enough time, or you wait and look at long enough distances, then this is all you should care about. You should only care about conserved densities, because everything else dies down at those scales. I mean, there is a caveat here, is that if you have symmetries in your theory that are spontaneously broken, then you also have certain goldstones which are massless, and they can also propagate over long distances. But that's a caveat which can very easily be put back into the system, so I'm not going to worry about that too much. Okay, so once you have set up this paradigm, the characteristic coefficients or the characteristic parameters of your model is essentially how the essential conserved quantities move about in the fluid. And these are characterized by certain transport coefficients. Most usual example you would probably know are viscosity of a fluid or a conductivity of a fluid, which will tell you how stress or how stress would move if you were to like strain the system, or how particles would move if you were to introduce new charges into the system. And like once you have that, you can write down the classical conservation equations for these conserved charges, and they will, for instance, this is a conserved density if you want, and the dynamical evolution of the conserved density is given by the flux, the divergence of the flux, where flux is given by certain constitutive relations which has this transport coefficient sigma, which is conductivity in it. And this you can use to determine the classical evolution. However, this paradigm seems to be a little too simple for if you wanted to actually go much non-trivial from this. I mean, hydrodynamics is a very old field, right? It existed almost 100 years before the first field theory was ever written, and for most purposes, it does a very good job. But we as physicists are very hard to please, because we always look for things where things break down. And eventually we did find out where hydrodynamics breaks down almost 50 years ago in 1970s, where we started seeing that if you waited a little too long, then hydrodynamic description starts to break down. Is that what you thought, that all of these classical equations will determine your long time behavior, long range behavior, it will start to break down if you started to wait a little too long. And the reason for this is stochastic noise. So, I mean, you remember, like I just said that there are these other degrees of freedom which are not conserved. Let me call them microscopic degrees of freedom, and they don't propagate over very long distances. So I have, like, let's say like each of this mode is these blue lines here, and they don't propagate over very long distances. On the other hand, this conserved a thing will move to very long distances. However, even though these microscopic things don't actually move very far, they can affect the motion of the long wavelength fluctuations just via interactions. So these small guys can interact with this large mode and eventually change its behavior if you accumulated it over very long times. And this is essentially the reason why if you waited a little too long, your hydrodynamic description will break down, because these microscopic effects, which are not very large, will start to add up.
Question?
And this is what led to what are known as long time tails in hydrodynamics. I'll come back to it, what these are. But this is the qualitative picture that hydrodynamic description will break down if you waited too long, just because of thermal noise. Well, okay, so what do we do now? Because the whole point of this exercise was that, well, maybe I don't know anything about the microscopic theory. So I just write down certain conserved equations, conserved charges, and I start to build up these models called hydrodynamic models. Well, you can actually get a lot of mileage by just assuming that this stochastic noise that is in the background is totally random. Like, you don't know anything about the microscopic theory, but you can imagine that this noise that is coming in is entirely random just because of statistical fluctuations. Any fluctuation that can be present in the system will probably be present. And I'm going to make another assumption that this noise is Gaussian, which, well, why not? And as it turns out that with these assumptions, the strength of this noise, or the free parameter that will be present in this by introducing this noise, is actually fixed by the so-called fluctuation-dissipation theorem. It essentially tells you that fluctuations of noise, or the strength of noise, is related to how your system is dissipating. This is a very general theorem in thermal field theories, and it tells you precisely what this noise should be. So, well, you don't actually lose much by introducing this noise into the system. And what you can do then, you can perform, instead of computing this any classical trajectory, excuse me, of your particle, you can perform averages of all classical trajectories over all configurations of noise. And this would lead to the physical, this would allow you to, in some sense, model the effect of microscopic noise on macroscopic fluctuations. This is a very
yeah. Sorry. Well, I don't know if there is a different policy in these seminars. Maybe Pepe might correct me, but there is a question in the chat. I think people can just ask, right? Or
yeah, I cannot see the chat, so someone can just.
Yeah. So that's.
My suggestion was that the questions in the chat could be deferred to the end.
Ah, okay. Sorry.
Of course, everybody is entitled to ask at any time.
Okay. Well, what I'll do is I'll pause at some logical points during the talk, and then you can ask me questions.
Okay. No. Okay. I just sorry.
In any case, since we have paused already, you can tell me what the question is.
Yeah, and I can also tell you a small question I have, but let's see the chat one first. But okay. So they are asking if there is a characteristic scale which tells when classical hydro breaks down and long time tails become important.
There is a classical scale. I forgot the name of that scale, but the scale will be set in essentially. I'll talk about it more when I go along, but the scale will be set in by essentially a scale of dissipation, essentially. So you will start. So essentially in diffusion model, the scale is set by diffusion constant. Because that's the only scale that is present in the theory. So you can construct time scales out of that, and you will eventually find that this is where these things will start to break down. But I'll be more precise. I'll have equations eventually because it's a theory.
Okay, I interrupted you. Well, also let me say that there is 3 people that have their mics unmuted, and I don't know if they are aware of it.
Okay.
No, because I'm hearing some noise.
Yeah.
So you comment here that the strength of noise is fixed in terms of the dissipative transport coefficients. Can you elaborate on that?
So I have introduced Gaussian fluctuations in my theory. Now Gaussian fluctuations will have some strength because that's the whole point. And all I'm saying is that fluctuation-dissipation theorem tells you that these Gaussian fluctuations will actually be fixed in terms of the strength of the Gaussian fluctuation is given by, for instance, viscosity, conductivity, and bulk viscosity, shear viscosity, and these things. Again, I'll make this more precise as I go.
Thanks. Sorry for the interruption.
No worries, no worries. Anyway, so the point is, okay, this is quite sketchy, but just to tell you a little bit about how precise this can be made, you can actually write down a Feynman diagram approach for computing these stochastic fluctuations, and this works actually very well. And just to give you a qualitative picture of how well it works, you can try to compute the correction due to due to the stochastic effects to conductivity. I'm going to define conductivity as the imaginary part of the retarded two-point function or the response function. This is pretty much the definition some people use. And the leading order contribution comes from the transport coefficient conductivity. But then you start getting this correction. And this correction is given by a certain coefficient A, which is some combination of some thermodynamic things. Chi is a susceptibility. Lambda is some transport coefficient that is related to the derivative of conductivity and so on. But the idea is that there is this correction here, which comes about just because of stochastic corrections, stochastic effects in your hydrodynamic model. This will not exist in classical hydrodynamics. And one physical effect, what you see out of this is that there is a fractional power of omega sitting here. And what that fractional power of omega tells you is that if you were to go to position space, or then when you go to late times, the correlations don't actually drop exponentially as you would expect in a hydrodynamic system, but they only drop polynomially. So this is what is known as long time tail, is that if you go to far enough long times, you'll still see these correlations coming from the perturbations you might have introduced in the very beginning of your experiment, but you were expecting them to fall off exponentially by this time. So this is like was done in like 1970s again, and like we pretty much understand, or at least we hope we understand how this works. Okay, well, so the point of today's talk is to try and convince you that even this is not enough. Even this picture is a little too peachy. And the first, hint you can probably guess is that, obviously, I assume the noise to be Gaussian. Right? The noise could be non-Gaussian, and that is obviously something we should worry about, and I will worry about it eventually as I go through my talk. However, there are even more subtle problems, is that even if you were to assume your noise to be Gaussian, you start to run into problems, because fluctuation dissipation theorem on its own does not uniquely actually fix the strength of the noise. It will fix to certain, so if you were looking in a quantum field theory picture, you have these pointed interactions. You have 3-point interactions, 4-point interactions, 5-point interactions, and so on. And what fluctuation dissipation theorem will do, it will fix all 3-point interactions, but it is not sufficient to fix 4-point interactions. And again, I'll make this more precise. So what this does is that it allows some free parameters in your theory that are not fixed in terms of hydrodynamic constitutive relations. And these free parameters will start to contaminate your low energy behavior. And this is what I'm referring to as the non-universality of hydrodynamics, is that noise, this is the strength of noise, these macroscopic effects that you thought were not important will start to actually show up in the low energy physics in terms of new free parameters that you might need to tune or might need to measure to be able to build an experimental setup or a theory which you want to apply to certain systems. And again, just to give you an idea of how these guys show up, in conductivity, they show up at much subleading order in the derivative expansion. This is typically the characteristic of these corrections would be, they will show up much further in the derivative expansion. So you can still trust your hydrodynamic model or the universality of hydrodynamic models up until this point where this correction set in. But once these corrections set in, these new coefficients are no longer completely determined in terms of classical hydrodynamics. For these new coefficients, you need to take into account some new free parameters that are no longer fixed in terms of the classical hydro. So I'm going to call them stochastic transport coefficients. So you might hear this name quite often during my talk, but this is a general idea. Okay, well, So since I'm talking about this topic for the first time, I'm at the risk of actually never reaching to the end of my talk. And if that happens, I just want to tell you the take-home message already. So the take-home message that I am trying to advertise here is that hydrodynamics, whether classical or stochastic, is not a universal description of long-range late-time physics. I mean, it is a pretty universal description, but it eventually breaks down. And like any effective theory, it has a regime of applicability, but here this regime of applicability is also in terms of these energy scales. Even if you go very, very far into IR, you will still be able to observe these non-universal effects if you want it to be a little too precise. As long as you are still okay, you don't care about those derivative corrections very much, you are still fine. I mean, this is good. I mean, I'm not saying that hydrodynamics is going to become unusable or anything, but it is always good to know the limits of your theory, so that you know where you should apply it and where you should not apply. So late-time correlation functions, particular, will get contaminated by stochastic transport coefficients, and these transport coefficients correspond to some microscopic structure of the many-body system, which you thought was not important, but it actually is. And stochastic transport coefficients are more than just some theoretical, I don't know, mumbo jumbo. I mean, they can actually be experimentally measured if you were to design careful experiments, but I'm not an expert on that, obviously. And just to highlight a point here, most of the things that I'm going to say here are actually directly applicable to other high energy or condensed matter scenarios where non-equilibrium thermal effects are important. Just like you have to like take into account some other degrees of freedom corresponding to maybe spontaneously broken symmetries or other, maybe, I don't know, photons and something for magnetohydrodynamics. But most of the ideas that I'm going to talk about will carry forward to almost any condensed matter system that you can think of. Good. So that was basically a long introduction of the ideas that I'm going to talk about. What I'm going to do in the rest of the talk is essentially flash out what I've said so far and give more details into the things that I've derived. I'm going to review first the classical and stochastic formulation of hydrodynamics, because probably not every one of you is aware of the machinery that goes in. But once that is done, I'll change focus to the more recently formulated SCHWINGER-KELDYSH hydrodynamics. This has recently only been developed in the past, I don't know, 5 to 7 years. And this is a formalism that allows you to actually keep track of all noise or all thermal noise in a systematic manner. So you actually don't have to introduce them by hand anymore, as you did in stochastic hydrodynamics. Once that is done, I'll talk about the signatures of stochastic transport coefficients that you can that I just flashed out in a little bit more detail, and then just essentially give a wrap up. So yeah, so this would be my logical point in case someone has any questions regarding the general structure that I gave so far before I go into the details. No? Well, okay. In that case, I'll just go forward. So yeah, classical and stochastic hydrodynamics. So classical hydrodynamics, as hopefully many of you are aware, is essentially just a set of conservation equations. So what you do is you see, okay, what are the global symmetries of your theory, of your system you might be interested in. If it's a fluid, I mean, it's a relativistic fluid, you might have a Lorentz invariance, you might have a particle number conservation, you might have other symmetries depending on the system you are interested in. It could be a Galilean fluid, it could be a fluid which does not have any momentum conservation. If it's, I don't know, a crystal. And in various different situations, you have different symmetries. And so let me just like flash out something for a relativistic fluid, which I very often work with. So it will have a conserved energy momentum tensor, and it will have a conserved particle number current. And what you do is like, okay, you say that, okay, your fluid is some macroscopic system, but you assume that your fluid is out of equilibrium, but it is still sufficiently close to equilibrium that you can actually isolate these small domains called a fluid particle, that each fluid particle is still in some sort of thermal equilibrium with its surroundings. So what each fluid particle can do, it can exchange energy, momentum, particle number freely with its surroundings, but it is still in a thermal equilibrium with its surroundings. Also, since it can actually freely exchange particles from its surroundings, it's actually better to work in the ground canonical ensemble and work with the intensive variables. So that's what I'm going to do. I'm going to work with fluid velocity, temperature, and chemical potential, which are the intensive variables corresponding to energy, momentum, and particle number. And so these are the usual degrees of freedom that you use in hydrodynamics. What you will do after is that, okay, you probably want to, is this me? I think so. Okay, sorry. So what you want to do is you also want to introduce some background sources corresponding to the operators that you're interested in, which will be energy, momentum, tensor, and charge current. And once you have all of this in your hands, you will write down the most general, what are known as constitutive relations, which is the most general expression for your energy, momentum, tensor, and charge current in terms of all the degrees of freedom that you just introduced and all the background degrees of background fields that you introduced. And you're going to just say, okay, this is the most general expression that I can write down, and this is what is going to characterize my fluid. When I put them back into these conservation equations, then this will give me some dynamical equations for these degrees of freedom that I introduced. Although, I mean, I say the most general, but obviously most general means most general, so you can write down whatever you want. And you probably don't want to do that because then it will take you forever. So what you will do is you will constrain these express systems, constrain these constitutive relations within what is known as a derivative expansion. So what you will say, okay, well, first I'm going to write down everything that does not have any derivative in it. Then I'm going to write down everything with one derivative in it, then with two derivatives on it, just because I'm going to assume the derivatives are small, things are not changing too much. Then I'm going to restrict this by putting some phenomenological requirements on it. First of all, is obviously the symmetries that I had in my theory. So I'm going to make sure that these expressions are Lorentz invariant. And then there are more subtle requirements, such as the second law of thermodynamics, which means that in each of these fluid particles, since I'm assuming them to be in thermal equilibrium, the entropy can only be produced. It cannot be reduced. And there are more subtle things which are Onsager reciprocity relations, but I don't want to go into that. Okay, well, so once you have that, you want to write down these constitutive relations. And actually, as it happens, most of what I'm going to say in this talk, or most ideas that I want to get across, I don't really need the full hydrodynamic model for that. So I'm just going to focus on a single U1 charge. So I'm going to assume there does not exist any energy momentum conservation. The only thing that there exists is a particle number conservation, a U1 particle number. Generalization to full hydrodynamics is actually not that hard. But okay, if I only focus to this one conserved charge, let me call this particle number, then the density I can write down as some function of mu, the chemical potential, and the flux will be given by some derivative of mu, and then E here is related to the electric field associated with the gauge field that I introduced. And you can go back on the scratch board and actually check that these are the most general constitutive relations you can write down at one derivative order. There's nothing else you can write down. And this coefficient sigma that appears here is known as conductivity. And this is a toy model of hydrodynamics. In hydrodynamics, you have other transport coefficients as well. You have viscosity, bulk viscosity, and a shear viscosity. But here I just have one transport coefficient. And what it tells you, this is essentially J equals sigma E. You might have seen this very often. And this also tells you that the same transport coefficient appears as a gradient of chemical potential. And okay, well, I'm just going to state a fact that second law of thermodynamics requires that conductivity has to be positive. Don't want to go into that. Okay, well, okay, once I have this equation, I can, once I have these constitutive relations, I can set up this equation, which was a conservation equation. And what this equation tells me is that if I were to start with some initial configuration, of chemical potential at some point in time, let's say t equal to 0, then this equation will tell you how chemical potential evolves in time. And eventually you can solve this differential equation and figure out what the chemical potential should be at any given point in time for a given background field configuration. Simple. And what you can do is you can define expectation values of these currents that are introduced here for this classical configuration in the presence of these gauge fields as essentially just J mu evaluated on the classical configuration. Nothing to worry about this. But okay, then I can start asking some fancy questions, and I can start asking what are the response functions. A response function is essentially how your expectation value responds to change in the background fields. The first one is essentially how J responds to the linear response. J, this guy 2-point function, is known as a linear response function. Then you have cubic response functions, you can have quartic response functions, and so on and so forth. And you can actually derive all of them by just taking this expectation value that you just defined and perform variational derivatives with respect to the background sources that you had introduced. And the only reason I flash them out is because these are the things you can actually measure in an experiment. You can tweak your background fields, that you can tweak your electric field, which you are imposing on a physical system, and you can measure these things by studying the response the system shows. And these coefficients are actually the things you can go and measure in lab. So these are the things I will focus on. So for instance, the 2-point function, the prediction for 2-point function by this model that I just showed gives you this guy. It shows that it has a pole. This is called a diffusive pole. D is given by some ratio of sigma and chi. Chi, I will remind you, is the susceptibility, sigma is the conductivity. And this 2-point function has a diffusive pole, and the strength is given by conductivity. And similarly, you can write down a 3-point function. I've written down for a special values of frequency and momenta. And the 3-point function similarly has a form. The form itself is not very important. The only thing that is important is that you can actually derive these. And you can keep deriving these for all higher order interactions, all higher order response functions as well. So an important thing here are these ellipses, which are possible corrections to these guys. And the corrections, at least in this formulation, can only come through high derivative corrections to the constitutive relations. And just because derivatives always appear in integer numbers, these corrections will always be positive powers of omega and k squared. And this is something that will break down once you introduce stochastic fluctuations. So good. Now I'm going to introduce stochastic fluctuations. And what that means is that I'm going to allow for this noise that can stay in the background and see how this will actually affect my classical trajectory. And what I'm going to do for this purpose is introduce what are known as microscopic microscopic in this current flux. So Ri is a microscopic flux contribution to Ji, which is not a function of mu in the same way. This is just something random coming from the microscopic theory, some random contribution. And what I'm going to do is I'm going to solve the same conservation equation in the presence of this R noise source. What this will allow me to do is compute these expectation values in the presence of background gauge field and in the presence of some noise R. Then what I'm going to do is I'm just going to average over all noise configurations with some Gaussian strength factor lambda. So lambda is just a matrix, so it will be like, because R is a vector, I have a matrix strength here. And all I'm doing here is performing a path integral over all configurations of R. And this gives me the quote-unquote stochastic expectation value. And well, once I have that, I'm going to use the exact same formula I had before and compute all the response functions. And I'll ask you to trust me for now that this actually reproduces the long time tail results that I introduced in introduction. I'll come back to this as well in a little more detail as I go through. Okay, well, this is probably the most technical slide on my presentation. And what I'll try to convince you is that this same thing that you just computed by just performing averages over all noise configurations can be made into a more formal field theory that you might know from your courses on quantum field theory. So what I'm doing in the first step, let me just take you through it. Shouldn't take a long time. What I'm doing in the very first step is just, first of all, doing the usual QFT trick, where I can take any expectation value and change it into a variational derivative with respect to some gauge field, some background field, by introducing a coupling term. So this is all I'm doing. In the second step, what I'm doing is, because this is a classical expectation value, so here I have assumed that equations of motions are already satisfied. So I'm going to undo this by introducing a Lagrange multiplier phi a and writing this equation. So phi a just makes sure that the equations of motion are satisfied. And this allows me to actually take mu off shell. So essentially performing the path integral over phi a will restrict mu to have the classical configurations. So this is all I'm doing. This is just, essentially entirely equivalent. Well, then what I'm going to do is just take this JR and use this decomposition in terms of R in the classical part. So I have a J mu and a R, which is a noise piece. And what you can see is that, okay, once I have this form, the assumption of Gaussianity becomes important, because I had assumed my noise was Gaussian. So I have an R square piece here and an R piece here. And this is a path integral that you can actually formally do. And you can perform this path integral, not a very hard exercise, and you can derive the last line. And in the last line, you will see the form of it is pretty much what you would see in any quantum field theory. You're performing some variational derivatives of log of some path integral. And this path integral computes for you the generating function of hydrodynamics, and these things in the bracket here can be identified as the effective action of hydrodynamics. And this was some work done in 2014 and 15 by Pavel and some of his collaborators. So, okay, I have this, and I can again use one of the formulas that I had in the past of performing variational derivatives of this guy to compute response functions. And again, the response function is given by one variational derivative with respect to this subscript A gauge field, and a couple of variational derivatives with respect to the usual gauge field of this effective action that I've just introduced. So this is something that I'm going to come back at many times during the talk, is this effective action. And essentially what I would like you to, appreciate is that I have taken this hydrodynamic theory, which I started from scratch in terms of equations of motion, and I have lifted this into a bona fide effective field theory with an effective action.
Sorry, can I ask?
Yeah.
So the dependence of this effective action on mu, you are not showing.
So yeah, so mu will appear inside the J, and will appear inside this lambda coefficient as well.
Through the constituents relations?
Yeah, so it will appear in J mu through the constitutive relations, and in lambda, just because lambda can be arbitrary.
Okay.
Yeah, by the way, it's actually a better idea if you just, people should just stop me for questions, so that people don't have to actually wait till the end if they have any doubts. That could be a better strategy. Anyway.
Can you say again why lambda depend on mu? Sorry.
I just took lambda to be arbitrary. So lambda could be a constant.
Okay. So why?
It might not be. I don't know. I'm just saying it could be anything you want. I'm not restricting it because I have no reason to.
Okay.
Okay. Well, in that case, let me come here and actually come to lambda. So I just said lambda could be arbitrary. So what I could do is I could write down a sort of constitutive relation for lambda as well, and expand it in derivatives of mu. So the first term will be just some diagonal term with some coefficient c, and then you can write down some derivative terms. One of the first term that you can write down is this del I mu. There can also be gauge field dependence, but I'm just not writing those terms right now because, simplicity. But now comes almost the main player in the game, which is the fluctuation dissipation theorem, which is a theorem which tells you that the two-point symmetric function of any two operators is related to the retarded function or the response function by this formula. This is a very well-known formula. It has even a Wikipedia page for it. And what you can do is you can go back and compute this. These are both the things that you can actually compute using your effective theory that I just wrote down. Response functions, the way I just told you, and the symmetric functions are very easy to compute anyway. And what you will see is that this will restrict you that C must be related to conductivity, sigma. So it's just a relation, and this just has to be true. So the C guy to respect fluctuation dissipation theorem must be same as conductivity up to the temperature. On the other hand, there have been generalizations of fluctuation dissipation theorems. Now we have fluctuation dissipation theorems for almost, not almost, for all kind of endpoint functions, not just the two-point functions. And as it turns out, the three-point functions, the symmetric three-point function is again fixed in terms of the retarded function. So you can fix all three-point interactions, but 4 and higher point functions are no longer fixed. So there is an ambiguity in this theorem. So the 4-point symmetric function is not fixed in terms of the 4-point retarded function anymore, because there are other kind of orderings that you can do in that. For multiple point functions, you can do partially retarded functions that are not retarded in all points, but only some of them. And those things also become important. So when you go 4 or higher point interactions, FDT, or fluctuation dissipation theorem, is no longer sufficient. And this is precisely the origin of stochastic transport coefficients, because you cannot fix this coefficient θ1 in terms of fluctuation dissipation theorem. And this will be left arbitrary. And this will be the origin of, this will be an example of a stochastic transport coefficient. But the Schwinger-Keldysh formalism that I'll talk about now will make this more precise. Okay, this will be another natural point. In case there is any question, I would take it now, because this is going to get slightly technical.
Yeah, can I?
Yeah.
Yeah, just a quick question.
Mm-hmm.
Physically, what does fluctuation dissipation theorem correspond to? Does it mean you to be in thermal equilibrium or perturbing around?
Yeah. So yeah, so fluctuation dissipation theorem means that I'm going to stay. So it means that the background state that I'm perturbing around is the thermal state. So the background state is a thermal state, and then I'm performing fluctuations over the thermal state. So fluctuation dissipation theorem tells you is that the thermal noise that is present in your system in that thermal state is actually proportional to how much your system is going, how much a small fluctuation is going to dissipate. So a dissipation associated with any small fluctuation is related to these thermal noise that is present in the background. But yeah, this is an assumption about the fact that I am perturbing around a thermal state.
Okay, thank you.
Yeah, if I were to perturb around any general state, not a thermal state, then fluctuation dissipation theorem will not exist. So this is especially a statement about fluctuations around thermal states. Okay, well, so this is the Schwinger-Keldysh formalism of hydrodynamics. So, well, just to retrace back a little bit, I wrote down an effective action for you. And while I could derive that effective action, started from some scratch, starting from some equations of motion that we usually use for hydrodynamics. This is not, the best thing a theorist would want. First of all, there is no first principle understanding of what kind of noise is allowed, what kind of noise is not allowed, and how would you go about introducing these noise degrees of freedom into hydrodynamics based on certain symmetries. There is no variational principle understanding here. So for instance, I just introduced chemical potential as a degree of freedom, but you could ask, okay, if chemical potential is a true degree of freedom, then can you do like a variational derivative with respect to mu and write down this noise equation of motion? And no, you can't. So chemical potential is not the true degree of freedom in your theory. Then there are more subtle questions like how something like a second law of thermodynamics emerges from this effective description. And this again is not clear in this classical picture, I mean, in this EFT picture that I just wrote down. And more formally, we know that there is a real-time formulation of thermal field theory, and we would like to understand how this hydrodynamic framework is related to that. And well, these are questions more than these are motivations, and I'll try to answer some of them, but I'll ask you to trust me on the others that almost all of these questions can be answered to some level of satisfaction in the Schwinger-KELDYSH framework of hydrodynamics. Okay, so this is what we have. Again, I'm going to only focus on a single U1 charge, but it can be very easily extended to almost anything. So, okay, this is my field content. So I'm going to introduce a phase field. This will be a U1 phase field, just a scalar field, and I'm going to introduce a noise partner of that field. Physically speaking, if you are aware of the closed time path formulation of thermal field theory, then this essentially corresponds to the fact that you start with the density matrix at some t equal to minus infinity. You evolve this density matrix to some late time, and in the meantime, you and this is the part of the contour on which this like one combination of field lives. And then what you do, you back evolve this entire thing to come back to rho beta, to your density matrix, and this is where the other part lives. And this is just, I mean, when I saw it the first time, it did not make any sense to me. So I don't expect it makes a lot of sense to a lot of people. But in case it does make sense to someone, this is the closed time path formulation of thermal field theory. And in a nutshell, you can think of this phi r as a true physical degree of freedom, the true phase field, the U1 phase field that you're interested in, and phi a is the noise associated with it. So every degree of freedom has noise associated with it. This is the idea. In the same Schwinger-KELDYSH spirit, I will introduce two gauge fields. I have done them already in my past formulation, but now there is a subscript r sitting on one of them. But this is just a representation thing. You can ignore that r subscript for the most part. And what you can do is, again, these two guys are coupled to two currents. One of them is called the R current, and one of them is called the A current. Nothing too fancy about it. But just to tell you a little bit, the chemical potential that I used to have earlier is related to this field phi r just by this. So mu is mu naught, which is the equilibrium chemical potential, plus the time derivative of this R field. And so essentially the time derivative of R field is the fluctuation in the chemical potential around a thermal state. On the other hand, the classical constitutive relations are just given by this R current that I have here, and I just restrict to this configuration where I just set everything phi, everything A to 0 and everything R to just without the version with R. And good. You can compute all the response functions again in the very same way. You can take this effective action that you would write down using these fields. You can perform a path integral, and you can perform variation with respect to this A and R background fields. This gives rise to some function, and then the retarded and the symmetric functions are two special cases of these functions that you can write down. And a lot of this discussion can be found in this 2011 book by Kamenev. But okay, this is the interesting part. The interesting part is that actually this is the field content, but I mean, any effective theory has two components. It has a field content and it has symmetries. So that was the field content bit, and this is the symmetry bit. First, I have a U1 global symmetry, which is like you allow your theory to be invariant under arbitrary shifts of both the phase field and the associated noise. It's a global field because it can be compensated by a corresponding shift of the gauge fields that you introduced in your system. Then you have a spatial shift symmetry. The shift symmetry corresponds to the fact that your U1 symmetry is not spontaneously broken. I can say more words about it, but I don't need to for my purposes. Then there are a bunch of symmetries that, at least the first normalization, reflectivity, and positivity. They were introduced in this 2015 paper by Hong Liu and collaborators. And again, I can say a lot of more words about it, but the slide is just to like give you a picture that this can be made very, very precise. And finally, the most interesting symmetry for me is the so-called KMS symmetry, Kuba-Martin-Schwinger symmetry, if you want. And the symmetry is a discrete symmetry. So it's a discrete symmetry which almost looks like parity, but it's not, because it acts differently on the R fields and the noise fields. And if you're aware of thermal field theories, and this is related to the KMS symmetry or the KMS condition in thermal field theories. But at least this is the symmetry that will ensure for you that the fluctuation dissipation theorem at the full nonlinear level, 2.3, 3.4 or whatever, is always satisfied in your effective theory. Again, I don't expect you to understand any of this, but just for you to have an idea that you can actually have a set of symmetries that will make what you're going to do very, very precise. And this is what that precision. Yeah.
I got a bit confused about this two-phase symmetries. So the global U1 is there because you have a theory with like U1 charge. Right?
Yeah. So I mean, I have a global U1 and then I have a noise U1, but they are just two copies of the U1.
Okay. So in this line here, this is both how the noise transforms and also the normal, let's say.
Yeah, I mean, so there are three U1s if you think about it. There are two U1s in the first line, which tells you that the phi R, the phase field, and the associated noise both shift under the U1.
Okay.
And then there is a more weird symmetry, this one. But this is something that I mean, if I can just tell you that if you were to lift this symmetry, then you end up with the effective theory of superfluids rather than fluids.
If I leave it, no, say again.
If you lift it, so I mean, if you don't impose the symmetry, then you will get a superfluid, and if you impose a symmetry, then you get a fluid.
Okay.
I mean, physically speaking, what I can tell you is that typically a phase is just a field, right? So I mean, you can start like, I mean, let's say that you started at some initial configuration, at some initial time slice, and you have this phase field, but you can always redefine what you mean by a phase, because that's in your hands. But you can only do it at the initial time slice. You cannot keep doing it forever and ever and ever. I mean, if you know what a phase means initially, then you should not change the definition as you move through time.
Okay.
And this is the symmetry that is this symmetry.
Okay.
But on the other hand, if you were in a superfluid phase, then the phase has a physical meaning. Then you cannot redefine it anymore. And so that's why in a superfluid phase, you will not have the symmetry.
Mm-hmm.
So these are the three U1s. The other are just. Anyway, so the point is that, okay, well, I have all my symmetries, I have all my fields, so let me write down my effective action. And as it turns out, the effective action that I wrote for you before is essentially just this. It's this written in a more compact notation. I have defined these B fields, which are just a linear combination of A fields and the gauge field. And these are by construction gauge invariant. The chemical potential I already defined for you. It looks like I forgot the mu naught here, but okay, this is a chemical potential. And the time derivative of this BR field is actually, you can find out it is this combination. And you can plug all of these things in here. And this is precisely the effective action that I wrote down for you before. So this is the effective action that you get from stochastic hydrodynamics is essentially can also be constructed using this EFT formalism, using the Schwinger-KELDYSH formalism. It is not very hard to see that this is actually KMS invariant. It's not very manifest here, but you can perform the symmetry, and you can justify for yourself that L1 is actually invariant under KMS. So it satisfies fluctuation dissipation theorem to any arbitrary order. But then comes the important part, is that even though L1 is the effective action for, I mean, is the same effective action that we wrote down before, it is not the unique effective action. because you can actually write down more terms that are allowed by the Schwinger-Keldysh framework, but they don't show up in the classical formulation. And again, you don't have to look too close into this, but L2 is an example of such a term. It's actually the most similar term that you can write down at third order in derivatives. And θ1 and θ2 here are two arbitrary transport coefficients, which are not fixed by classical hydrodynamics, which is just L1. And I'm going to call θ1 and θ2 stochastic transport coefficients. Just to illustrate to you why this is not classical, I just said that if you start with L1, you can differentiate with respect to the A fields, the A field here, to get JR, the R copy of currents. And this is a very trivial exercise you can perform. You will get this. And then if you further set all the A type fields to 0, you should get the classical constitutive relations. And this is what you get. And if you look what del T BRI is, it is just this guy. So you can convince yourself that this is precisely the constitutive relations I started with. So you can get classical constitutive relations by starting from the effective action, performing a variation with respect to the A type gauge field, and then setting all A type fields to 0. And this is a mechanism that keeps working even in full hydrodynamics. So you can get the energy momentum tensor again by this mechanism. If you were to do the exact same exercise with the L2, the point is L2 is at least quadratic in A type fields. So even if you were to perform a variational derivative with respect to the A type gauge field, you will end up getting something that is linear in A type fields. So when you switch off A type fields, you get 0. This is the reason why L2 is purely a stochastic effect. It does not show up in classical constitutive relations at all. By extension, θ1 and θ2 are purely stochastic transport coefficients. They don't show up in classical constitutive relations at all. And these will be the ones that I'm calling are making your hydrodynamic description non-universal. Okay, I don't know. I don't have much time, I guess. How much time do I have practically?
You can wrap up in 5 minutes or so.
Okay, I try my best. So, okay, so in this last part, I'm actually trying to show that this is not just some formal thing. You can actually use this. And how you can use this is you can start with an equilibrium state. In my case, equilibrium state can be some density, or even if you wanted to work with chemical potential, you could. It's easier to work with density, at least for this part of my talk. And you can say that, okay, N, your density is some N naught plus some del N, some small fluctuation. Phi A is just phi A, and I'm going to turn off gauge fields because I don't care. And I can write down, I can take this L1, that was my effective action, and I can perturbatively expand it in these fields. So the first part of this will give me a quadratic action, and this is the free action. I mean, in your QFT business, in your QFT language, this is the free part of the effective action. You can take this and you can do the inversion in momentum space, and you can get propagators. So you get a mixed propagator, which tells you how N relates to phi A field, and this has this diffusive pole. And you have another propagator, which is the symmetric propagator for N, and this is this guy. And this is something very easily computable. But the more interesting part is that you can start from L1 free, and you can keep expanding it in further higher orders in fluctuations, phi A fields in del N. And you can get this 3-point interactions and 4-point interactions. And you can actually build up a bona fide quantum field theory. You can keep doing that, 5-point, 6-point, 7-point, whatever you wish. But it's, as always, hydrodynamics is an effective theory, so you're going to truncate at some point. So let me truncate at 4-point here. And this is the effective theory. But on the other hand, the L2, which I wrote down, the stochastic part, it only starts from 4 points. It does not actually have any 3-point interactions in it. You could go back and look at it. And it starts from the 4.1 and it leads to these 4-point vortices. By the way, this is related to the fact that fluctuation dissipation theorem fixes everything up until 3-point interactions, which is the reason why stochastic effects, or the purely stochastic effects, only start showing up at 4-point interactions and higher. And these, and quite easily, these contributions do not show up at tree level classical retarded correlation functions, just because these are purely stochastic effects. And you can actually start doing some really fun calculations. You can start computing the 2-point Green's function. And the 2-point retarded Green's function, as I defined for you earlier, it was given by the 2-point retarded function is an RA kind of function, just to show you a little bit. So the retarded functions are all R and all the other legs A. So you will perform one variation with respect to the A field and one with respect to the R field to get a retarded response function. And at tree level, this reproduces for you the classical result that I had flashed out in the very beginning of my talk. But at one loop order, you can actually write down some more fancy Feynman diagrams, and you can actually compute these Feynman diagrams, and you end up getting this result. And you can see that there's a square root here. And if I expand the square root in small k, small momentum, then I will end up getting a fractional power of omega. And this is a fractional power of omega, which gives rise to the long time tails that I talked about initially. And this was a calculation that was done very recently in 2018 by Sean Hartnell and some of his collaborators. Okay, well, what about stochastic coefficients? Well, once you put in the stochastic interactions, you can actually write down more diagrams. Turns out there is no diagram at one loop order involving these vertices, but you can do a 2-loop diagram. 2-loop calculations are not fun. I can tell you from first-hand experience now. I had never done that before, but you can do these calculations and you can actually work out these. Okay, they don't look so bad once you finish doing them. But essentially, the idea is that you do get a contribution from these diagrams to the 2-point functions. I mean, what that contribution is not actually that important compared to that you actually get such a contribution. So that means that the 2-point functions actually get contaminated by stochastic effects. So this will be like the take-home message. But in any case, the conductivity, if you were to define the imaginary part of it, the conductivity gets a contamination at the order of omega squared to the power 4. And this was the thing that I illustrated to you in the very beginning. You can do more fancy things. You can compute the 3-point functions. And then, I mean, the only reason I did that is because I could do a 1-loop calculation to compute the correction to the 3-point function. And again, similar kind of story exists, is that you do get a correction to the 3-point function due to this 1-loop diagram, which involves a stochastic transport coefficient. Anyway, so just to wrap up, the stochastic signatures that I talked about are actually very suppressed. They're suppressed for 2 reasons. One of them is that they just show up at higher order in the derivative expansion, but they are also suppressed because you are performing these loop integrals. And whenever you perform a loop integral, you perform integrals over momenta, and the higher the number of dimensions, the more momentum suppressed loop becomes. So, well, if you wanted to experimentally measure them, or hope to measure them, then you would probably want to like relax the suppression somehow. I mean, the easiest way to relax is to actually do this in lower number of dimensions. So you do it on a thin film or something that will relax for you. On the other hand, there's a more interesting thing is that most of this talk, I only talked about a U1 charge. I did not talk about momentum fluctuations. As it turns out, then when you introduce momentum fluctuations, you have this thing called a convective term, which is U del U term in the equations of motion in Navier-Stokes hydrodynamics, or even in relativistic hydrodynamics, which gives rise, which essentially tells you that this interaction vertex that I have here, I mean, probably don't remember from my short version of it, but as it so happens is that this interaction vertex actually shows up at previous order in the derivative expansion compared to the ones it shows up in the U1 model. And because of that, actually also, if you were to take into account momentum interactions, these effects get risen to higher orders in the derivative expansion. So just to give you a small table, U1 d equal to 3 is probably one of the worst models to study these interactions, but you can go to the full hydrodynamic model. It is still incompressible. I have not taken into account the ballistic sound mode into this computation. But whenever you go from left to right, you relax 2 powers of momentum. Whenever you go from top to bottom, you relax something you relax a little bit in the loops. So d equal to 2 is very interesting, by the way, because you get these log divergences. They are present in this paper by Sean Hartnell. And you can do the same in d equal to 1. And this is just like a power counting argument. And it will show you how suppressed these stochastic effects will be. Cool. So I'm just going to flash out the slide that I had in the very beginning because I did make to the end of the talk. So that's nice. So again, hydrodynamics is not a universal description for long-range late-time physics. You do get these stochastic effects, which I'm calling coming from stochastic transport coefficients that will contaminate your long-distance late-time physics. And these microscopic coefficients can be understood as some manifestation of the microscopic noise or some microscopic effects, or at least how these effects are like showing up in, or how they are interacting with the long-range modes or the conserved modes. Stochastic transport coefficients are in principle at least physically measurable, but I'll need to think, or someone will need to think a little bit more carefully about the ways these experiments can be set up. And finally, just to again emphasize that most of these effects will show up in most condensed matter systems or most high energy systems wherever finite temperature or non-equilibrium effects are important. Good. Thank you.
Thank you, Akash. That was very nice. Are there more questions for Akash?
I have a question here.
Yeah.
So do you think that the additional stochastic terms that you're introducing can be mimicked by introducing in the standard stochastic formulation some very complicated kind of noise, not Gaussian, but some very complicated?
It could, I mean, in principle, yes, but I would not know in that, because I mean, a very important part of introducing the Gaussian noise was that you were able to perform certain path integral. So there was a certain path integral that you wanted to compute to actually arrive at the effective action here.
Right.
And if your noise is not Gaussian, in principle, I see no obstruction, but in practice, maybe you won't be able to perform that path integral to arrive at the effective action. That's, I mean, that's the only thing, I mean.
But perhaps one can leave the effective action with the noise terms, and then these loops will have these noise fields also running in. Like, why do you want to, is it necessary?
I mean, yeah, it's just, I mean, you could in principle leave the effective action at this level of the first line here. I mean, the second line here.
Yeah.
I actually don't know what would be so bad about leaving it there. Just that perhaps, I mean, the only thing probably will be important, even if you introduce such non-Gaussian noise, is to make sure that fluctuation-dissipation theorem is satisfied. And as it turns out, in the representation that I have the effective action in the very last line, fluctuation-dissipation theorem can be implemented more properly just because I have this doubling of degrees of freedom. So I know what are the correct degrees of freedom now in terms of a closed time path. But in the second representation, I probably wouldn't know how to actually restrict this noise and how to impose fluctuation-dissipation theorem.
No, I agree that this formulation is like very systematic way of doing things.
In principle, again, I don't see any problem in doing that, but in practice, I don't know how you would actually go about it.
Okay. Thank you. Thank you.
Hi.
Hey,
Hi. Yeah, I have a question concerning the terms you wrote down.
Yeah.
New stochastic. They looked, I mean, most of them looked like analytic in omega and k, right? There were just some powers in omega and k.
These corrections?
You had this table, and this one, for example, is two-loop correction looks also.
So this is actually analytic. So as it turns out, the two-loop correction is analytic. But I mean, as it turns out, like each loop has omega to the power half non-analyticity. So two-loop corrections are actually analytic, but you can do the similar three-loop calculation, and that will be non-analytic.
Right, but then the question is, I mean, wouldn't this mix with terms which are anyway there in the hydrodynamic derivative expansion?
I mean, they would, yes. So this is one of the interesting pieces, right? That they would mix with things that will come from the hydrodynamic derivative expansion. But what is interesting about this is that those coefficients or those those eventual things in the response functions are not the same things that show up in the classical constitutive relations anymore, because now these effects are actually contaminated by these by these stochastic transport coefficients. So you cannot determine them, or in other words, you cannot determine the classical constitutive relations by measuring these response functions in lab.
Right.
That's just the idea.
And the other question I have is, I mean, you worked out very nicely this this U1 model, which basically is the diffusion equation, right?
Exactly. Yeah.
So now diffusion equation is of course fine, but say from a relativistic standpoint, it's not that good because it's causal. It has modes which propagate.
So
light one. So usually you can cure that by modifying the diffusion equation to this telegrapher's equation, where you have a second pole, not only the diffusion pole, right?
But I mean, by the way, most of what I'm saying here can still be done for, let's say, Galilean hydrodynamics. So Galilean hydrodynamics does not have the problem. You can do that for relativistic. For Galilean hydrodynamics does not have that problem, the causality one, obviously.
Right, but you can still do it. I mean, people did it even before the new relativity introduced the relaxation time for the current, because the physical argument is that the current doesn't build up instantaneously to the response. It takes some time and some memory function or whatever. And then my question is, if you take such additional modes into account, would this modify these terms which you have here, or would be not modified by?
So typically what you have to do is, I mean, typically what is important is that you just have to construct an effective action starting from these principles. And what if you wanted to add such a term, you have to still make sure that it is respecting these symmetries. So most probably, as far as I am aware, adding such a term, or adding a term which leads to an extra pole, leads to another term whether that is quadratic in B80 here, or so in principle, yes, you can add such terms. That would be my answer to your question. But again, whenever you add those terms, you have to be careful that any such term that you add is compatible with these symmetries, because in particular the KMS symmetry, because KMS symmetry is the one responsible for fluctuation-dissipation theorem. So as long as you make sure that whatever term you add to your setup is KMS consistent, then this is consistent with fluctuation-dissipation theorem, and most of my story should go through.
Okay, thank you.
Cheers.
So you showed at the beginning dependence, which was fractional powers of omega. Now I see some square roots in your expressions.
Okay.
Should I consider this exotic or what? This square root that you have there?
So this square root, this is the full answer that you actually get from here. The answer that I showed in the beginning is the small momentum limit.
Okay, so that square root is the omega to the 1/2 you mentioned before.
Yeah, so that is because I Taylor expanded this in K.
Okay. Is there some physics in the funny analytics? I mean, the fact that you have cuts.
Yes, so this corresponds to the fact that
particle production or something. Should they?
Yeah, so now you not only have poles, but you also have these branch cuts in the omega space. So this paper by Sean Hartnell and collaborators, it has a very good discussion about this. I know Luca Delacretas has also given a lot of talks about this. So yeah, there are now branch cuts in momentum space. Unfortunately, I don't know much about what they actually end up doing. But yeah, it's I mean, what they definitely end up doing is the long time tail behavior, which is essentially that if you were to fully transform this back into position space, you no longer have, I mean, this function is not analytic in omega and k anymore. So that means that when you do this Fourier transform, you don't get an exponential fall off anymore. You get more complicated things.
Mm-hmm. Okay, are there more questions? Okay, so if not, I would like to thank Akash again for his talk.
Thank you very much for having me.
And thank you very much. I'm going to stop the recording now.
Yeah, thanks.